Okay, so basically what we're covering is material that can be found in chapter 8 of your book. And it's linking those things that we have been doing to rotational motion. So if we do a review of everything that we have done so far, we did kinematics. And our kinematics gave us V final is equal to V initial plus acceleration times time. We got V final squared is equal to V initial squared plus 2 times my acceleration times my change in position. Then we had our change in position was equal to our initial times time plus 1/2 our acceleration times time squared. And then our rotational one was the same that we had so we saw this nice parallel of everything that's what we've actually been working with. Now, once we did this, we went to forces and we had our net force was equal to our mass times our acceleration. And we ended up doing work, and work was our force with a dot product times our distance. And this was work was force through a distance. We had our conditions of equilibrium, which is the sum of the forces was equal to 0, and this was an equilibrium item. We had potential energy of a spring. We had potential energy due to gravity. We had kinetic energy. We had a couple other things. We had our force due to gravity, our universal law of gravitation. G is m1, m2 over r squared. We had that. So we have these kinds of items that we were dealing with, and we had momentum. We had some conservation laws. We have conservation of mass. We have conservation of energy. And we had conservation of momentum. Well, chapter 8 is going to give us this idea of what happens if we're starting to rotate things. So we are actually going to define something called torque. And torque is going to be a cross product. All right. And it's a cross product of our distance and our force. This will be a vector product. And this is force acting at a distance. So we get something that's a little different because that is actually a vector quantity. Instead of mass here, we're going to get this idea of a moment of inertia. And that is going to be dependent upon how the mass is distributed. And so we can have moments of inertia that are different for spheres, different for point masses, different for disks, different for a variety of things. And in fact, I'm going to reference your chapter right here, you have a table in your book. This is table 8.1, and it's got different moments of inertia depending upon how the object is there. Because we all know that if I'm rotating my object or I'm spinning my object, and I'll take my cell phone as the example, if I'm spinning it around this axis, that's different than if I'm spinning it around this axis, or if I'm spinning it around this way, or if I am spinning it around this way. So I have all kinds of different axes here that cause things to spin differently. And how my object is going to behave is going to be different based on that moment of inertia. So moment of inertia is really going to act like our mass. We're going to get torque in terms of a cross product. We also get torque in terms of our moment of inertia and our angular acceleration. So you see that our net torques are going to be very similar to what we have for our forces. So we see some parallel items there. So you can look at things that are a little parallel. I want to get my other items right there where we want to cover that. So we'll have that moment of inertia, we get that. Then we will also have our kinetic energy. Now, kinetic energy of rotation is going to equal 1/2 I omega squared. So again, you see that if I'm rotating, I have to deal with my moment of inertia, and I'm dealing with my rotational item. So this is my kinetic energy of rotation. We don't really have anything related to this, but I do have angular momentum. And we don't call it P, we actually call it L. And that is I omega. So we get that I omega, and we still have our conservation of momentum. So this right here gives you a nice review of everything that we have dealt with or are about to deal with in terms of what's going on, except for some stuff that we get with our fluids and everything. But this is also why for Physics 1, there is no way to not have a comprehensive exam, because this is what we started with. We're still working with that. We're still working with it here, except now we bring it into rotation. But now we have all of these things. And then I do have my one other condition. The summation of the torques are going to equal 0 for my second condition of equilibrium. So you've got this gives you a nice, really nice summary of the equations that we've been dealing with. Okay, so let's go ahead and look at these now. We're going to start out with torque. And what we just said is that torque is going to be a vector quantity. And we talk about it being at a distance. And I want you all to know that D cross F is not equal to F cross D. All right? These aren't equal, because watch what happens. We've all seen this before. And I have a wrench. There's my wrench. And if I apply a force to my wrench, and this is my distance away, if I'm applying my force this way, I am going to get a rotation in that direction. All right. So if I'm applying my force, I'm going to rotate my bolt in that direction. So if I rotate my bolt in that direction, my bolt is going to come out of the paper. I'm going to unscrew it out of the paper. Now, if I do the same thing, we're going to take the same situation. I'm going to put my wrench on here. There's my wrench. Now I apply the force in that direction. The bolt is going to rotate that way. The bolt rotates into the paper. So this is where the right-hand rule comes in. I'm coming up. This gives me the out of the paper. I'm going, if I'm doing it this way, I'm going into the paper. That's why these aren't equal, because my directions, and we by definition have this as the positive direction. Counterclockwise is positive. Clockwise is negative. So by applying my force, if I'm taking that wrench and I'm applying that force, it goes in. And just like what we saw with work, if I were, if we go back to our shopping cart, and I'm applying my force here, we know that the biggest bang for our buck is what was in line. So when we did our work, we look at it that way. Same thing here. Our biggest bang for our buck is if we're at a right angle to our item. And so we can actually F, or this D cross F is going to be D force sine of the angle. And so if we did this at an angle, we're going to reduce it because we're going to get the biggest torque by being perpendicular. Now, our units are going to be meters, newtons, but we usually write them as Newton meters. And this is not a joule, because we've seen this before. If I'm in English units, this is going to be in foot pounds. And we've seen that before, but this in an SI units, we usually write them down as Newton meters, and it is not a joule. This is also a vector quantity, and it's going to be a little bit different from dealing with our item. So let's go ahead and let's calculate a torque. So we're going to use this distance as 30 centimeters. So this is going to be a 0.3 meters. All right. And we're going to apply a force of 50 newtons. And we want to calculate the torque. Well, this one, since this is at a right angle, we're going to have our 0.3 meters times our 50 newtons. And that's going to equal That's going to equal 15 Newton meters. Now, what would happen if I change this up? So I'm going to have we're going to represent my wrench like this. I'm going to represent this as we're going to apply a force this way, and that's going to be 15 degrees. And here's our bolts. This is still going to be 0.3 meters, and our force is going to be 50 newtons. So the torque is going to be dF sine of the angle. This is going to be 0.3 times our 50 newtons Now I'm going to do the sine of 15 degrees. And this is going to be 3.88 Newton meters. So we've all done this before. And now this one, if I am applying this, okay, if I'm applying this, the rotation is going to go this way, and that's going to be a positive, and it's going to be a counterclockwise rotation, and we would be able to calculate our torque. All right. So that gets us started with our rotational items. Now, and I don't know if you've ever seen it before, but if you take a can, so I have a can, and my can has, say, minestrone soup in it. This is going to roll differently than if I have a can that has condensed tomato soup in it. It's going to roll differently because I can look at the items in the can. So in one case, my can is going to act like a solid. So this would be the condensed soup. In the other case, I might have a lump here and a lump there and a lump there. And this would be my minestrone. And we've seen this before. So for example, if I have a mobile and I have my fish here, my big fish, and over here we have a series of little fishies. We know that I can be in equilibrium if I can look at my center of mass. And that's over this item. And we've seen this before. If we go out to Monument Valley, you will see things that look like this. I've got a big, huge boulder over here, but it looks like most of the boulders hanging off to the side. And it's all balanced on one point, but it doesn't fall down. That's because the center of mass of that object is being supported underneath my clip. And you can demonstrate this for yourself. Let's take a table here, and we can put a book on the table and it's not going to fall off. We can actually put another book on the table and it's not going to fall off. And we could eventually, depending on the book, we could eventually have a book that's totally over here. But if each one of these, when we get our center of mass, and as long as our center of mass is supported by the table, it's not going to fall off. And we played with that over and over again. So let's calculate a center of mass. So I'm going to take a series of objects. I'm going to have a big mass here. So this is going to be 5m, and it's located at 0, or at we're going to have it at 3, 0. I'm going to have an object at the center of mass, or at the origin, and we're going to call that one M. Then I've got an object here that's, we're going to make it 6M, and it's going to be located at 1, 3. So I've got 3 objects. My center of mass is going to be defined as this object for the center of mass in the x direction is going to be the sum of the individual masses and their x position divided by the total mass. So my total mass for the system is going to equal m plus 5m plus 6m. So that's going to end up being 12m. So if I want to calculate the position of my x, I'm going to do my first one was at m, and it's located at 0. My second one is at 6m, and it's located at 1. And my third one is 5m, and it's located at 3. And it's all going to be divided by 12m. So this is going to equal 6 plus 15 divided by 12. My m's all cancel out, so I don't have that. So I get 21 divided by 12. So my x is going to be at 1.75. I can calculate the y, and you're going to follow the same procedure. Now this one is at 0, so m is at 0. My 6m is at 3. And my 5m is at 0. And it's all divided by 12m. So I'm going to have 18 divided by 12. And that's going to be at 1.5. So I can actually draw my center of mass on this one. So I'm at, if that's 1.3, this is going to be, here's my 175. And the other one is at about there. So this would be the location of my center of mass. And note that your center of mass does not have to be physically on the object. Now, if I had a uniform sphere, okay, well, actually, let's do a cylinder. So this is a uniform cylinder. We have pretty good experience on where the center of mass is because we can use symmetry to get us there. And we can actually look it up and we can do that symmetry. So we know it's going to be on this axis in the middle. We know it's going to be about halfway up. And we can actually guess where the center of mass is going to be if this is a uniform cylinder. But like we said, if I was looking at my rolling objects, how these are going to roll or spin is going to be very different than where our center of mass comes from. So let's kind of look at that for a second. We're going to actually calculate what we call the moment of inertia. My moment of inertia is going to be defined as our sum of our individual little masses that we have. So let's take a baton. And this baton here is going to be, we're going to do 3 m's for this side, 3m for that side. We're going to do 2m for this one, 2m for that one. And each one of these items is going to be a distance r. So this is a baton. So first, let's calculate the center of mass. All right, I can calculate the center of mass. So if I'm doing my x position, And this is we're gonna make this as x is equal to 0 right here. So this x position is gonna be 3m, and it's at minus r. These two are at 0, so they will not contribute. And I'm gonna get 3m at r, and then I've got a total mass is 2 plus 2 is 4, and 3 and 3 are 6, so this is 10m. My center of mass is 0 for the x, which is what we would expect. We can do this for the y one, and we can get 0 as well. But if I'm going to spin this object, things are going to be a little different. So what I'm going to end up doing is the moment of inertia for the baton is going to equal the individual. It's going to be the sum of all the little moments of inertia. So if we're going to rotate it this way, so we're going to rotate it around the axis of the 2m, I'm going to get my 3m, and it's going to be at minus r squared. I'm going to have my 2m at 0, plus my 2m at 0, plus my 3m r squared for that side. So I'm going to end up with 3m r squared plus 3m r squared is going to give me 6m r squared. That would be my moment of inertia for the baton if I'm rolling it around that axis. But what happens if I rotate it around this axis? Well, I'm going to follow the same pattern. My moment of inertia of the baton about that axis is going to be my 3m minus r squared plus my 2m r squared plus my 2m minus r squared plus my 3m r squared. So I'm going to get my m r squared, because each one of those are going to be there. So I'm going to get my 3 plus my 2 plus my 2 plus my 3. And I'm going to end up with 10 mr squared for my moment of inertia doing it about this axis versus doing it about that axis. And you have an example and the example is 8.12 in your text. So you've got that example. So let's do, we'll do a cap on that here in just a minute. We're going to do one more thing. So again, table 8.2 or table 8.1 has different moments for different objects. Now, we said and defined it very early on that my angular momentum, this is angular momentum, is going to be defined as the moment of inertia times my angular velocity. This is our ice skater problem. So if I have an ice skater, the mass of my ice skater is going to be 65 kilograms. And in the mass of my ice skater over here is still 65 kilograms. If I'm rotating at an angular velocity of 3 radians per second, and we're given an R of 1.5 meters, and then here we've got an R of 0.75 meters, we want to know what the new angular velocity is. Well, my moment of inertia or my angular momentum can be written as we can do this as mr squared omega is equal to mr squared omega. Masses are the same, so those go away. This one has my 1.5 squared omega is equal to my 0.75 squared omega. We know what this one is. This one's 3 meters or 3 radians per second. And this, now we're going to divide by our 0.75 squared, and that's going to give us our new one. And we've all seen the figure skater, right? It's going to end up being faster. This is going to end up being 12 radians per second. We can also calculate the kinetic energy. So let's do the kinetic energy of this 1/2 I omega squared. And we're going to do this for our 1.5 meters. This is going to be 1/2 my 65, my 1.5 squared, and my 3 squared. Kinetic energy is going to be $658 joules. All right, let's do an equilibrium problem. So we're going to get a Planck. And our Planck is 2 meters long. And we're going to put an object here at the very end. That's 25 kilograms. And we're going to put an object, and this is at 0.25 meters away from this end. And this is 35 kilograms. We want to set our pivot here such that our thing will balance. All right. And we want, so we know that if we're from this be a distance D, and we've got this will be at some other distance, we're going to call this X. We know that I've got to have the torque on this side has to equal, because it's going to rotate that way, and it has to balance out with my torque on that side so that it balances there. So we've got some things that we need to know. So we've said that this is 2 meters. We've got this placed at the end. So really what we have is we have our Planck we know the center of mass of our plank is going to equal at 1 meter because it's a uniform bar. And we've got to put this piece there such that our pivot is over the center of mass. So we can actually do that. So let's find our position, the center of mass of the system. And we know that our 25 kilograms is at 0. Our 10 kilogram plank is at 1. And our 35 kilograms is at 1.75 because it was a 2 meter plank and we subtracted off 0.25 meters. And my total mass is 25 plus 10 plus 35. So we're going to get 10 plus this is 61.25. And I've got 35 plus 35 is 70. So I have 71.25 divided by 70. That's going to be at 102 meters. That's where we would place that pivot. And now we can calculate the torques to see if that's the case. Okay, you can actually calculate the two sides to be able to do that. But you all have played with this before. You know, you've done this kind of a teeter-totter problem. If I'm balanced on the center of mass of my teeter-totter and I have a kiddo who's sitting here and is at 45 kilograms, where does this kiddo have to sit if this kiddo is at 55 kilograms? We want to know that distance away. Well, if this is 1 meter, we want to figure out this distance D. So this side is 45 times 1. This side is 55 times D. I'm going to get my 45 divided by my 55, and that's going to give me my D. And that's going to be at 0.82 meters from the pivot. Because this side will want to rotate this way, this side will want to rotate that way, and we can balance it out. Okay. So now we're going to kind of combine this all together. We're going to do a merry-go-round. So we have a merry-go-round here. And we're going to have it rotating in that direction. And initially, it's going to rotate at, we're going to have it rotate at 5 radians per second. And it's going to be at a constant rotation. The mass of our merry-go-round there we go, is going to be, we're going to make it 65 kilograms. It's going to have a radius of, let's make it 2.5 meters. We're going to put a kiddo here, and this kiddo has a mass of 30 kilograms, and that kiddo is going to be at 1 meter away. And we have another kiddo that's over here, and this kiddo is going to have a mass of 80 kilograms, and it's at the 2.5 away. And we're rotating at 5 radians per second. So we want to calculate the initial moment of inertia. We're going to calculate the initial kinetic energy. Then we're going to calculate the new angular velocity when the big kid jumps off. So let's look at the moment of inertia before. This is going to equal the moment of inertia of kid 1 plus the moment of inertia of kid 2 plus the moment of inertia of the merry-go-round. This is going to be mr squared for kid 1. This will be mr squared for kid 2. And this will be 1/2 mr squared because our merry-go-round is going to act like a disc. And for a disc, it's going to be 1/2 mr squared. And then we'll calculate the moment of inertia after. And that's going to be our kid 1 plus the disc. So let's go ahead and calculate this out. So we've got 30 times our 1 meter squared plus 80 times our 2.5 meters squared plus our 1/2 65 2.5 meters squared. I'm getting 733. And this is going to be in kilograms meters squared. This one is going to be our 30 times our 1 squared. 1/2 mr squared for the other one. So I've got my 65 times my 2.5 squared divided by 2 plus 30. And now I've got 233 kilograms meters squared. We have conservation of angular momentum, so I get I omega is equal to I omega. This is initial, and this is going to be final. So I get I initial divided by I final. Omega is going to give me omega final. I initial was 733 divided by my final, which is 233. And we started out at 5 radians per second. And now we're going to be going at 15.7 radians per second. So that gets you kind of a nice idea of how to work some of these problems that you've got. All right, I think brains are full. Do I have any questions?